Hello friends, in this quarter we are going to deal with simple harmonic motion. Here in this quarter I am going to deal with free oscillations, damped oscillations and forced oscillations. Probably this will run into 4 parts. These are the reference books recommended by the university for students to refer to. In the first part I am going to deal with free oscillations. I would like to list before you the topics that we are going to deal with. These are oscillations. What are oscillations? What are damped oscillations? Then basic definition of oscillations. We shall try to understand Taylor series in a mathematical way, and then we shall apply that to the motion of simple pendulum, and we shall conclude that simple pendulum exhibits simple harmonic oscillations. Then we shall write the differential equation for simple harmonic motion, and then we shall devise the solution of this second order differential equation of simple harmonic motion. Then we shall understand the exponential form of the same equation. We shall understand the time period equation, and finally we shall conclude this part with energy of harmonic oscillator. To understand what are oscillations basically, we shall roll through this video, which will offer you a very clear idea about what we are discussing. And I would like to mention that these oscillations we are observing in our day-to-day life, but I want to make it clear that what we are talking of. Here we are having a spring. That spring is offering tension with this arrow that we are calling restoring force. Here we have a yellow shaded block which is composed of some massive material like iron, and this is placed on some ice block. Then the weight of this block, this heavy block, is acting downwards, and that I'm calling weight of the box. Then the reaction from classical mechanics, you must have understood, reaction of the table or this ice block is directed upwards, and there does exist friction between this block and ice. Maybe because of the presence of ice, friction is small. If you are having a wooden block, friction will be higher. If it is in air, friction will be minimum, and if it is in vacuum, friction will be almost zero, depending upon the level of vacuum. When the block is moving, it possesses kinetic energy. When the block is at the extrema of the spring, either right hand side or left hand side, it is having potential energy. So the restoring force immediately acts upon in opposite direction every time. And here we have a bar indicating kinetic energy and the elastic energy that you can call potential energy. This spring is a kind of a linear spring that offers uniform linear tension through. Now the reaction is a force acting upwards, and here with time we have started the simple harmonic motion. Oscillations are taking place and amplitude of the oscillation is decreasing. Here you can see the kinetic energy is decreasing, and continuously amplitude of the oscillations, which has been recorded in form of the dots appearing on your screen, which is scrolling upwards, that has reducing amplitude. In this fashion you can see the restoring force becoming opposite, and friction force, friction force opposite to the restoring force and vice versa. So here the kinetic energy and the potential energy diminishes and the motion stops. This is the contribution of friction. Had friction not been there, then this motion would have lasted forever. But there is no physical system wherein we can have zero friction. We can make it as minimum as possible. Now, referring to the above diagram, you can see the oscillations. It is a repetitive vibration, typically in time, of some measure about the central value, often called equilibrium. So central position I'm going to call equilibrium, or between two or more different states. The term vibration precisely used to describe mechanical oscillations, and the examples are swinging pendulum, alternating current, and so on. In the last video, we have rolled this mass m on the ice cube which was attached to this spring, and the spring was attached to a rigid support. Now this spring has some constant we are going to call K, and now this is connected to a piston kind of thing, and this is dipped into a container containing some fluid, liquid, say water or some oil or so on. So when the ven is exhibiting motion inside the liquid, more friction is offered, and that causes damping, that slows down the motion, and the component that contributes to damping, slowing the motion, is represented by B here. So here damping has effectively appeared into our discussion, and this will diminish the oscillations quite fast than in the case we have seen in the last video. Now here I want to roll through a list of points. A simple mechanical oscillating system is a weight attached to linear spring that I have described to you while showing the video, and the subject to only weight and tension. Such a system may be approximated to an air table or ice surface. The system is in equilibrium when the spring is in static position, that we call equilibrium position or mean position. If the system is displaced from this equilibrium position, there is net restoring force because of the spring on the mass attached, weight attached, tending to bring the system back to the equilibrium. But when the system is restoring to the equilibrium position because of the mass involved in our discussion, that is weight involved in our discussion, which has momentum, gains some kinetic energy, and it goes in opposite direction, and that sets a kind of periodic motion which we are calling oscillations. Now the system where the restoring force on a body is directly proportional to its displacement. Now I'm going on, in the zone of technical things, and on the basis of these things I'm going to write equations and then later on solving them to understand this motion. So you have to be very attentive in understanding these arguments. the system where the restoring force on the body is directly proportional to its displacement. See, what I mean to say that force, restoring force is directly proportional to displacement. Displacement I'm going to chart in one dimension by x. Then the dynamics of spring mass system, which we have seen, are described mathematically by simple harmonic oscillator. Now, simple being the motion is simple, harmonic is the kind of mathematical component appearing into it that is being called harmonic, and oscillator means a system which oscillates about the mean position, goes to extreme right and extreme left, and it shuttles between these two extremas through mean position. And the regular period of the motion, the regular periodic motion by this virtue is called as simple harmonic motion. When the system makes a complete cycle, starting from one point, going to extrema, or returning back to the extreme point here, so that makes a complete cycle. So the time required for that we call period, and the motion is periodic because it is repeating over and over. Now the next point on our agenda is Taylor series. Let us suppose that f of x be a function defined in the domain of our interest. This function can be expanded around a point x equal to x0. x0, I'm charting some point where the function is present in the around region, which I'm calling domain. So by virtue of Taylor's theorem, we can express this function f of x. This function f of x we can express in form of Taylor's theorem in the neighborhood of the point x0. Let us try hands on this Taylor's theorem. This function f, I am writing f of x, here I am simply writing f, just a shorthand. So this is equal to the function at given point x0 plus first order derivative of the function at the point where we are talking about, that is x equal to x0, into x minus x0, how far you are moving away from the point, that to the power 1 upon 1 factorial. So this is not going to matter, power 1 and factorial 1, but the next terms are going to matter. That is why I have written it here, plus second order derivative of the function. So what is the meaning of derivative I want to tell you. So here f dash means partial derivative of f with respect to the variable we are talking about as x. So this one is f dash. Then we are talking about f double dash. So for this quantity we are making one more dash, and this is del 2f by del x square. So this is how second derivative we are talking about here. This is also worked out at the point of interest x equal to x0 into x minus x0 whole square. So how far you are going from the central point, that square divided by 2 factorial. And this series is infinite series wherein we are going to roll to the third derivative at the given point x equal to x0 into x minus x0 to the power 3 upon 3 factorial, and so on and so forth. And the last term is nth order derivative of the function at x equal to x0 into x minus x0 to the power n upon n factorial. Now obviously this is provided nth derivative of this function is valid and so on, but working out couple of derivatives will also solve our point of interest, and it will be quite well approximated for practical considerations. Now here you can consider for this present discussion, we can consider a simple pendulum which is a bob suspended by a string. So this is a fixed point which is a frictionless pivot, and a bob is suspended here, and it can be set into motion, and it can oscillate back and forth between two extreme positions through the equilibrium position. So the red line, this is indicating the trajectory of the bob. This is some equilibrium position which is indicated by the dotted line. At this time the string will be like this. So this bob is essentially massive, and the thread or the rod which we are considering for suspension is massless, or it should have negligible mass as compared to the mass of the bob. The red one, as I said, is the trajectory, and here the maximum displacement from mean position. So this is the mean position, and for example this is the maximum displacement. So this is called amplitude of motion. So amplitude of motion, I shall say A, which is the maximum displacement from mean position. You can consider it on right hand side or left hand side, does not matter. This can be charted nicely using this angle of oscillation, so it can be related both way. The another point of emphasis is that we are going to have energy considerations at the end of the discussion, but here I would like to show you some plots so that the dancing of energy, how it is going to happen, I can give a bird's eye view for that. So here I am plotting energy on y-axis and displacement on x-axis. So mean position is corresponding to 0 displacement. So this is the mean position. Then extreme position is this. For the bob it is here, and on the chart it is here. The another extreme position is here. On the graph it is at -1. So these are the correlations that I want to make, I want to establish between the physical experiment and the graph we are talking about. Now I'm interested in talking about the kinetic energy, and kinetic energy is minimum at extreme points. Bob is coming in this way, stopping momentarily at the extreme position and returning back. So kinetic energy of the system is minimum 0 at the extreme position. As the bob starts going towards the mean position, velocity goes on increasing, and so kinetic energy goes on increasing. At the mean position, you can mark this. The kinetic energy is maximum, and as it goes to right extrema, the kinetic energy goes on decreasing, and the bob momentarily stops and reverts back in its journey, and so on. This goes on happening, and the kinetic energy oscillates between 0 and 0 through the maximum value present over here. Now we shall try to understand the potential energy. The potential energy of the bob is minimum in this equilibrium position, and it can be shown here equilibrium position, and the red line which I am trying to highlight is corresponding to the zero energy. As the bob goes to right hand side, potential energy goes on increasing this way. So if I chart the baseline and the top line and set this as H, so MGH you can call rise in the potential energy. So as the bob travels on extreme right, potential energy goes on increasing. When the bob returns back, the potential energy again goes on decreasing, reaches to minimum, and when the bob travels to left extrema, the potential energy once again increase to the maximum value. And if you add potential energy and kinetic energy, you obtain a straight line that indicates that the total energy of the system remains constant during oscillations. Here you can see the examples of simple pendulum. So a bob is oscillating about the mean position. So here you can mark the baseline. So this is the baseline and this is the extreme line, and the another extreme is present over here. So here in this diagram, this is the rigid support and the bob is oscillating, and you can chart velocity. Velocity becomes minimum on the extrema, so you can see the vector vanishing, and acceleration becomes maximum at the extrema. Velocity becomes, you can mark this, velocity becomes maximum in the mean position, while the acceleration vector becomes zero at the mean position. So these are the simple harmonic motions exhibited in terms of simple pendulum. Related to that, we can have a simple circular motion which can be used to correlate the simple harmonic motion cycles. Now here we are coming back to the topic of Taylor's series, and the function that we have discussed for writing Taylor's theorem or Taylor series, we are going to reserve to represent potential, and obviously the potential V is function of x. However, I have written only V. You have to understand that V is function of x, and the functional dependence I have written as f of x. So this is a function defined in a domain of interest where the things are all right as regards to derivative and all that. This function can be expanded around a point, say x equal to x0, by Taylor's theorem, and that is, we can write V is equal to V at x0, that is Vx0, plus derivative of V with respect to x. So V is function of only x, so I am not using partial differentiation sign here. So dV by dx at x0 into x minus x0 plus d2V by dx square at x0 plus, into x minus x0 square upon 2 factorial, and so on and so forth. It means that if we consider that x0 to be the origin of the coordinate system, that makes our discussion very simple. Then x0 is to be replaced by 0. It doesn't mean zero value. It means that you have to find out the derivative at x equal to x0 equal to 0. So by virtue of that, we can write potential V, which is a function in the given domain that is equal to potential at 0 plus dv by dx at 0 into x upon 1 factorial plus d2v by dx square at 0 into x square upon 2 factorial, and so on. You can go on writing infinite number of terms. However, for simplicity in our equations, we are going to consider first or second order derivative only depending upon the situation. Now, here the same equation I have rewritten in the compact form up to fourth order. The potential energy has a minima at the mean position that we have seen from physical examples. And now we want to relate the mathematics for the physical situations. At mean position, the potential energy has minima. So at the point of interest, x equal to x0 equal to 0, which is mean position, we have to have potential energy minimum. So the mathematical condition for minimum of the function is dv by dx is equal to 0 for minima or maxima, and for minima the second order derivative of potential with respect to position at the point of interest, that is x equal to 0, is positive. So minima is represented by second order derivative positive. So here we have v is equal to v0 plus this has vanished. So this is 0 because potential energy has minima at the mean position, plus k into x square by 2. So here k is being replaced. So I want to replace this second order derivative d2v by dx square by k. Now from mechanics we have F is equal to minus grad V. So F bar we can write for one dimension as minus times I cap into partial derivative of V with respect to x. So we have to operate minus I times partial derivative of first order of V, where this V we have picked up from this first equation. Now here we already know that the first term is 0 because when you operate derivative of v0, which is a constant quantity with respect to x, you ought to get 0. Then the second quantity is k. This k we have written, I'll highlight it separately. This is a k value, which is second order derivative. This I'm writing here. Actually, I want to highlight a factor that here we have this term vanishing out and the leftover v, which is v0 plus k into x square by 2 factorial and so on. These next terms, these are present here to represent v, and then we are taking partial derivative with respect to x of this quantity times minus I. So here we have already ignored this term in our next expression. Now force we are interested in finding minus I times partial derivative of v0. We have to work this out. Partial derivative of v0 with respect to x is 0. Then partial derivative of x square with respect to x will be 2x, and that 2 will be cancelled with this, and we are left with minus k times. So here we have minus I, and here we have plus I. So minus k times x upon 1 factorial plus, rather minus, so this minus sign is again appearing here. Here it has appeared. Minus k1 times derivative of x cube will be 3x square. So 3 will be cancelled with one of the 3 in the denominator, and we'll be left with minus k1 times x square upon 2 factorial, and so on and so forth. So what we have done here, we have considered terms up to this only. The higher order terms we are ignoring. We are ignoring all terms above this. And then we are left with f is equal to minus kx I cap. So here I want to emphasize upon a point that force is equal to minus k is a constant x I cap. If I want to write scalar form of this equation, I'm not writing vector. So f, you can see it is directly proportional to x. The constant of proportionality is k, and minus sign indicates that in simple harmonic motion, the particle is going on either side, and when the particle is going on either side, the force F is directed towards center. During this, the force is directed this way. So this is the mean point, mean position on which the force is directed, and it is indicated by the negative sign present over here. Similarly, the expression for V0 that we have considered on the last slide, I would advise you to go back to the last slide by pausing the video. You can record V is equal to V0 plus k times x square by 2 factorial, and so on. So here this quantity is 0 because first order derivative has vanished, and that is for here in red color the extrema, maxima, minima function condition of the function in the range, and minus pi by 4 this to plus pi by 4 has and no then we have the quadratic equations, or rather the Taylor series expansion of the same, where in the first constant I have selected all 1, the terms, second constant is 0 order, and third constant is also 0. That is culminating into a line left parallel to x-axis, V0 cutting y-axis at 1 plus k now, times this defines x square y-intercept, and by virtue of that, and we verify an equation of inverted the y-intercept is going correct or not. When we are writing expression for, then we can set a0 to parabola, a1 to minus 1 by 2. So that will completely match when we plot our diagram along to the cosine function in the given region of span minus pi by 4 to pi by 4 axis. And if we select then proper value position we have A2, stated it will further 0 is equal to 0 adjust itself, and this extreme to a right position is going this way. In this situation, V is equal to V0 plus k into x square by 2. Here y is equal to some constant, say a plus bx square. This is the equation of parabola, which is inverted, and that is for potential energy. So y is being replaced by potential energy and x is the displacement. So this is that inverted parabola which is representing potential energy. So here we are rewriting the conclusive equations wherein potential, which is function of x, is expressed using Taylor series, and for the potential to be minimum at the mean position, this factor is becoming 0, so this term is vanishing, and we are ignoring all higher order terms. So potential V is equal to V0 plus K times x square by 2. So this is our expression for potential energy. Similarly, the expression for force is I times, force is present only along x direction, either positive direction of x-axis or negative direction of x-axis, and this is equal to minus kx only, and here we are ignoring all higher order terms, and this quantity is already 0 because the derivative of v0 is a number that is equal to 0. So here the most interesting thing to note is that force is directly proportional to displacement. So this we have concluded from Taylor's series, and the force is directed in the direction opposite to the direction of motion always, and K is the constant of force. So this is the animation that is showing acceleration with letter A bar rather, and velocity vector v bar. Now here you can see the length of the vector v bar is minimum at the extremas, and acceleration is minimum at the mean position. Now this is the graph that is showing variation of potential energy with position. This is the equation that governs potential V is equal to V0 plus K times x square by 2. So V0 is something constant which is appearing here at this graph. This sometime you can consider 0, or you can have the definite assigned value, and this is having another term plus kx square by 2. So k by 2 you can consider another constant, and x square will represent parabola. So this parabola is opening upward on either side when the position is going on right hand side from the mean position and left hand side from the mean position. The force involved here is the one which is causing harmonic oscillations, and this is represented by minus kx I cap. So minus indicates that the force is directed always towards the mean position, and this force is directly proportional to the position. Now we shall raise the differential equation of simple harmonic motion. As we have stated, force is equal to minus kx I cap. Force is prevailing along x direction. Minus k has a significance. K is the constant of proportionality, and minus sign, as I said, it is directing the force towards mean position. Now force we can write from Newton's law, m into acceleration. So acceleration I am writing as d2x by dt square. This x is function of time, so I am writing x of t. So m into acceleration I have written as d2x by dt square. This x is function of time, that is equal to minus k times x of t. So here force is present along x direction and the displacement is caused along x direction. Therefore, we have switched to the scalar version of the equation. Now, we can rearrange this equation by taking minus kx on left hand side, and on right hand side we will have 0. So minus k will be plus k, and if we divide the equation by m throughout, we will have d2x by dt square plus k by mx, that is equal to 0. So here this quantity k by m we shall assign omega square, and that will lead us to a standard way of representation of differential equation that has got standard solution length. So here we have replaced k by m by omega square, and second order derivative is x double dot. So when a physicist is putting a dot on a letter, it means it is time derivative, and if there are two dots, then it is second order derivative. So x double dot plus omega square x equal to 0 is our differential equation, which is in the most compact form. Now friends, we are in position to attempt solution for the differential equation. So here we are at the solution of the second order differential equation. Differential equation is for simple harmonic motion. Now this is the equation which we have raised in the earlier slide, and this is the one we are going to solve. Now this d2x by dt square can be written as d2x by dt square plus 2 times dx by dt, and on the right hand side we have minus omega square x into 2 times dx by dt. What all we have done is we have multiplied the equation by 2 dx by dt on both sides. This we are doing for some special purpose, and now we want to integrate this equation d2x by dt square into dx by dt. This is being integrated over dt. 2 is constant, so taken out of the integration sign. Now minus 2 omega square is a constant on right hand side, and inside integration we are left with x into dx by dt. This is integrated over dt. Now the integration we have in the standard form 2 times 1 by 2 dx by dt whole square. So now if you differentiate this equation, you will be able to reach to this equation. So you can verify. Minus 2 omega square we have written, and then we have integration of this quantity which is appearing on this equation. This is 1 by 2 x square. So if you differentiate 1 by 2 x square, you will be able to reach to the earlier equation. So for this purpose we have done all these things by multiplying 2 dx by dt on both sides and so on. So here we can rearrange this equation as dx by dt whole square. This is equal to minus omega square x square plus constant of integration. This plus c is appearing as constant of integration. Now here we have started with this equation, and then we have ended up with this equation. Now as the potential energy is maximum at the extreme limit and kinetic energy is minimum at the extreme limits, we can handle this equation in this pretext from the physical situation. When x1 is equal to x2 is equal to the extreme position where the amplitude A is attained, then the velocity is 0. Now By substituting that, we can substitute dx by dt equal to 0. Here you can identify this, and that is equal to minus omega square. Instead of this x square, we are writing a square plus constant of integration. So here we can find out the constant of integration, that is omega square a square. So with this aid, we have solved the, or rather we have identified the unknown constant of integration in terms of known quantities, and the known quantity is omega and a, and the constant is omega square a square. Now x minus x0, rather x1 minus x0 is equal to x, that is equal to x2 minus x0. So we are considering identical conditions on right hand side and left hand side, and that we are representing in terms of a general variable x. And remember that this x is obviously x of t as we are considering, but for simplicity I'm simply writing that as x. So here we have the equation dx by dt whole square. This is equal to minus omega square x square plus omega square a square, the constant of integration we have introduced. And this dx by dt is actually, this dx by dt is velocity. So velocity square is equal to omega square. We have taken omega common, which is appearing on both the terms. So omega square into a square minus x square inside the bracket. So we are trying to simplify this equation and trying to extract some physical meaning out of it. So here velocity v, which is dx by dt, rate of change of displacement. So x is displacement and the rate of change is being represented by dx by, sorry, d dt, and this is equal to, so this is velocity square. I am trying to write velocity, that is equal to omega into under root of a square minus x square. So this is a very important equation. I'm going to rewrite this equation on the next slide. Here in the attempt of solving differential equation, we have velocity square, dx by dt square means velocity square. This is equal to minus omega square x square plus c, and velocity dx by dt, after resolving the constant of integration in terms of known quantities, we have that velocity equal to omega into under root of a square minus x square. Now this is again a differential equation of first order which is yet not solved. We have started with second order differential equation, and this is first order differential equation. Now we shall separate the variables. We are using the variable separation method to handle this first order differential equation, and dx is on left hand side. We are taking terms related to x on left hand side. So dx upon under root of a square minus x square, that is equal to omega times dt, that is equal to omega times dt. So here we have separated the variables. How we have separated the variables? On left hand side we have all variables relating to position, and in addition to position we have something which is a constant quantity, so we are not bothered. So on right hand side we have omega into dt, so there is no mixing of variables, and the variables are position and time. Now we can straightly integrate this equation. So integration dx upon under root of a square minus x square, this is equal to omega into dt. So this is sine inverse of x by a. So I'm I'm using the formula of integration, and this is sine inverse of x upon a. This is equal to omega times integration dt will be simply t, and we have some constant involved out of this integration that we are calling phase phi. So we can rearrange this equation, we can rewrite this equation as sine of, so see here, I shall try to rewrite this. So here x upon a we can write as sine of omega t plus phi. Now we can take this a on right hand side and we can write a nice equation which is solution of the simple harmonic motion differential equation DE-SHM. So x is equal to a times sine of omega t plus phi, where a is amplitude, this is the phase difference, t is the time variable, x is the position which depends upon time. Actually, this x should be written as x of t. So this is the very meaning of this x. So I would like to elaborate meaning of this equation, which is solution of the second order differential equation for simple harmonic motion. So x of t is instantaneous position of the motion. So you define the instant, the position will be defined. Then a is amplitude of oscillation, that is the maximum displacement from mean position. Then omega t plus phi we shall call phase of a particle at time t. As the time t changes, this phase will change. As this phase will change, sinusoidal of the phase will come into picture, which is multiplied by amplitude of oscillation, and that makes the solution of differential equation. So here phi we can call as initial phase. Here this whole quantity I am calling phase, and phi is called initial phase of a particle, and this initial phase of a particle is the phase of the particle at time t equal to 0, which can be also referred as epoch. So when you substitute t equal to 0 in this equation, whatever phase remains is phase at time 0, so that is initial phase. So friends, we have already solved the differential equation of second order, which is of simple harmonic motion, and that equation we are going to plot now. So the equation is x of t is equal to a sine of omega t plus phi, and for simplicity we shall consider a boundary condition t when t is equal to 0. When t is equal to 0, phi is equal to 0. This is the boundary condition. So with this we can write x of t is equal to a sine omega t, and here we have a sinusoidal function. Now if we choose a to be 1, so we can plot omega t on x-axis, and we have x being plotted on the y-axis. Now as the time rolls, you can see here that we are trying to plot a function. A sinusoidal wave pattern is being traced. Then for that, let's see it once again. Then when t is equal to 0, I am talking about another boundary condition. When t is equal to 0, the phase angle is pi by 2. Instead of being 0, it is pi by 2 now. So x of t will be equal to a times sine of omega t plus pi by 2, and sine of omega t plus pi by 2 is simply cos of pi by 2. So here you can see the variation of the x of t, x of t is being plotted on vertical axis and omega t is being plotted along horizontal axis. So the function behaves the way it is being displayed here, and the particle will exhibit motion when x is equal to 0, sorry, when t is equal to 0, cos of 0 will be 1, so the particle will start motion from this point. So you can see the animation here, how the particle is tracing cosinusoidal function. And this is in fact representation of what we have, a physical system that we call simple pendulum. So this is the bob which is being suspended by a string. So a bob is suspended by the string. So it is taken to the extreme position. So this is the maxima position on left hand side. This is the maxima position on right hand side. Or you can call the both the positions together as extreme position. And this is the mean position, equilibrium position. And when the object is at the extreme end, the displacement is maximum, that is A. So here for simplicity we have considered 1. So here when the phase is 0, you can see that it is like this here. So when the bob is displaced to maximum position, so it is going to this position. So it is again coming back to the mean position. So it is being represented here. Then it again goes back to extreme right and it is going here. Then again it is coming back to the initial position here. So that makes it here. So we have a complete sinusoidal wave to represent one cycle of oscillations. So same thing again I am trying to discuss with you, and here this time we have the equation being represented by x of t equal to a sine omega t plus phi, and same equilibrium position is here, and extreme right position, extreme left position. This is the generalized representation of the bob attached to a string, and as we travel, we make the bob to travel from one extreme position to another extreme position. We have sinusoidal representation, and as the initial phase varies, how the things behave I'm trying to show you. And in that we have this graph being plotted here using maple, and here this is the phase angle phi, which can roll from 0 to pi. So when it rolls from 0 to pi through pi by 2, this is the value pi by 2, then you will be able to see how this graph shifts. So here you can see when the slider is moved from 0 to pi by 2, it becomes cosinusoidal representation, and if you take it beyond, then the wave is further shifted. So this is the role of phase, you can understand. The solution that we have represented using the sinusoidal function can also be represented in the exponential form, and I want to show you that. So the solution that we are discussing is x of t is equal to a times cos of omega t plus phi, where the phi is initial phase and omega t plus phi, it makes a complete phase. Now we very well know that e to the power I theta is equal to cos theta plus I times sin theta. Then x of t we can write as imaginary part of the whole thing. So instead of theta, I am writing e to the power I times omega t plus phi. So this is my contention here, and this is to be multiplied by e. And e to the power I times theta is cos theta plus sin theta. I am interested in sine theta. Sine theta is a point of my interest. So I want to consider only imaginary part. So I am inside curly brackets, means I'm considering imaginary part of this. So only sine function I'm considering. So x of t can be written as real part of this. So that leads to the cosinusoidal solution. So in that situation, cosinusoidal means a cos of omega t plus phi. You can identify that. So this is the generalized representation of x of t as a into e to the power I times omega t plus phi. So obviously it is cos of omega t plus phi plus I times sine of omega t plus phi. So whatever solution you are interested in, you can consider using this exponential form. Now, time period we define as time taken by the particle to return back to the same point in the same state. Or we can define that time required for phase to increase by 2 pi. So here we recall this equation, differential equation of first order, where we have separated the variables. So x is on left hand side, time is only on right hand side, and we consider amplitude going from position going from 0 to a, that makes complete oscillation. So if you are considering a bob attached to a string, this is a string and a bob is attached to it, and from mean position we are going up to this position. So in this process we are having amplitude as a, and here x is increasing from 0 to a. Omega integration dt. So when I want to complete one oscillation, the time period is one complete oscillation. So I'm starting from here, one part, second part, third part, and then back. So that makes a complete. So here I'm considering only motion from this point to this point. So it makes 1/4 of the complete time period. So this is t by 4, where capital T represents period. So if we substitute the limits, sine inverse of x upon a is the integration. Upper limit is capital A, lower limit is 0. Omega times t, upper limit is t by 4, lower limit is 0. So sine inverse of 1 is equal to omega into t by 4. So sine inverse of 1 is pi by 2, that is equal to omega into capital T by 4. So t is equal to 2 pi upon omega, where omega is some constant we have started in the beginning of the differential equation, which was something like k upon m in the under root, where k is the spring constant and m is the mass of the bob. Now here we begin our discussion where omega square is equal to k by m and t is equal to 2 pi upon omega. So 2 pi into under root of m upon k. This being in reciprocal, we have to use this equation. So d2x by dt square is equal to minus omega square x of t. This is the basic differential equation. And omega square is equal to, we are forcefully rearranging this equation for omega square. So because we are interested in this omega, omega square is equal to 1 upon x d2x by dt square. So omega will be under root of 1 by x into d2x by dt square. So this omega is equal to acceleration upon x. Note that d2x by dt square, this is the acceleration quantity. So this quantity omega, which is acceleration upon x, this can be called as acceleration per unit displacement. Now we are interested in talking about energy of harmonic oscillator. The kinetic energy due to its velocity is 1 by 2 mv square. We all know it very well. Potential energy is due to the restoring force on every point x. So V is equal to dx by dt, that is equal to omega times under root of a square minus x square. Somewhere in the earlier slide we have done this. So kinetic energy is equal to 1 by 2 mv square. We are now interested in replacing this v square. So this is omega square into bracket a square minus x square. So at x equal to 0, the maximum kinetic energy is, so you can see here, this will be 0. So maximum kinetic energy will be 1 by 2 m omega square a square. When x is equal to a, then a square minus a square will be 0. So the kinetic energy is minimum. So we have nicely represented this solution of differential equation, which encompasses all the features that we envisage. Now, kinetic energy is this much. We have done this. Then potential energy is the work done against restoring force at the position. So work done is minus f bar dot dr bar. So minus of minus kx, force is minus kx into dx. So we are left with k times x times dx, that is dw. Now w will be integration dw, where the limits roll from 0 to x. We are interested in finding the potential energy at position x. So we are left with integration 0 to x kx dx, that is 1 by 2 kx square, because integration x dx will be x square by 2. So you can substitute the value of k from this equation. So k is m omega square. So we have work done also. So when x is equal to 0, potential energy, because this quantity being 0, potential energy will be 0. And when x is equal to a, potential energy will be 1 by 2 m omega square a square. So this x square is replaced by a square. Now the total energy is potential energy plus kinetic energy. So here you can see this. So this quantity and this quantity can be eliminated, and the total energy will be 1 by 2 m omega square a square. This remains constant during oscillations. So if a particle, if a bob is oscillating around this trajectory from one extreme position to another extreme position, the total energy of the system always remains constant. Sometime kinetic energy reduces to 0, then potential energy goes to maxima that time. Whereas when kinetic energy is maximum, potential energy will reduce to the minimum position, such that the total remains always constant.